Section 5.1, Sequences. This is from OpenStax Calculus Volume 2. At the bottom of every page is a link to where you can download the full textbook. So please do that. This is only to aid you as you go through that book, hopefully. Okay, so to begin with, a sequence is an infinite ordered list of numbers of the form a sub 1, a sub 2, a sub 3, 4, 5, 6, all the way up to n, and just continuing on. Now, each of these numbers is called a term. Okay, each of these is a term. And the symbol n is used as the index. Okay, it's the index variable for the sequence. We often write in these curly braces a sub n from n equals 1 to infinity to denote that sequence. Now, one thing to notice is this is a function, really. It's a function with a domain of 1, 2, 3, the natural numbers. Okay, that's all it is a function, but its domain is restricted to the natural numbers. So, for instance, let's consider this sequence right here. We have 2, 4, 8, 16, 32. You can write that as 2 to the n. Okay, the sequence and braces there. So that has two forms we could write. We say a sub n equals 2 to the n, or a sub n equals 2 times a sub n minus 1. That it's a recursive form, where it means we take the current term is 2 times the previous term. Okay, so we are multiplying by 2 each time, so that that follows through. So let's go ahead and look at a sequence here, 3, 7, 11, 15, 19. Write an explicit formula for this sequence. All right, so to begin, an equals, okay, our first term is 3, and it appears that it is increasing by 4 each time. So this is plus 4 times n minus 1. That is, plug the value of 1 in there. Plug for n equal to 1, that would be 3, which is our first term. Plug in a value of 2. That would be 8, or that would be 1 times 4, so that is 7. So that takes, the n minus 1 takes into account the fact that we're starting at 1. Now, if we rearrange that, that would be 4n plus, minus 1. 4n minus 1 is the explicit formula for that. Okay, number 2, consider 2, negative 2/3, 2/9, negative 2/27, 2/81. Write an explicit form. Okay, so the first thing I notice is that I am starting with 2. Okay, so this is 2. Now, in this case, this is multiplying by 1/3, it appears, each time. It's multiplying by 1/3 each time. Okay, and I'm going to go ahead and put the n minus 1 there. Now, there's only one thing that does not account for. That does not account for the changing of positive to negative, positive to negative. So I'm going to go ahead and make this a negative 1/3. And every time you write a formula like this, you want to take values of n and try that out and make sure that a sub 1 is in fact 2. If I plug in a value of 1, that is 2. Okay, if I plug in a value of 2, that is negative 2/3. Okay, that's good. So it does in fact work for that. All right, next. Negative 1/2, 2/3, negative 3/4, 4/5, negative 5/6. Alright, so it appears that our numerator is always the n value. So this is a1, a2, a3, a4, a sub 5. So the numerator is always that n value. So let's go ahead and say that's n. And the denominator is always 1 more than that, so n plus 1. Okay, now, the alternating pattern we've got, where it goes positive, negative, positive, negative, I'm going to use a negative 1 to the n. Now let's check that. If I plug in a value of 1, that is going to be negative. Okay, negative 1/2. That works. If I plug in a value of 2, that is positive 2/3. Okay, so that does in fact fit our sequence. All right, next we have number 4. Consider the sequence 3/4, 9/7, 27/10, etc. Okay, we have two separate things going on here. Two separate things going on. One of those is the numerators. The numerators are all powers of 3. Okay, so a sub n equals, and that is going to be 3 to the n minus 1. That way the first term is 3. Okay, that works. The second term is 9. Okay, that'll work. So we have this. Now the denominators, we have something different going on. We have 4 plus 3 times n minus 1. Okay, so let's rearrange that as 3 to the n minus 1 over 3n plus 1. That is our explicit formula for that. And again, plug values in and make sure that they match. And there's where you can go to get the textbook. Alright, next we have number 5. 1/5, negative 1/7, 1/9, negative 1/11. Alright, so the denominators, I see a pattern. The numerators, the numerators are simply going between 1 to negative 1, 1 to negative 1. So let's do a negative 1 to the n. And if I plug in a value of 1, that would be negative. Maybe I should make that an n minus 1. Let's try that. If I plug in a value of n equals 1, that is positive. That's positive. If I plug in a value of 2, that is negative. Okay, so it's alternating back and forth properly. Now the denominator is 5 plus, and it is increasing by 2, so 2 times n minus 1. So let's write that as negative 1 to the n minus 1 over 2n plus 3. That is our explicit formula for that sequence. Okay, next we have some recursive sequences. Okay, let's begin with A. A1 equals 2. So the first term is 2, and each term is multiplying by negative 3, that appears. So that is 2, negative 6, 18, negative 54. Right, so the way that we can write that is our first term, and then it's multiplying by negative 3, so that will be negative 3 to the n minus 1. Plugging in a value of 1, that is 2. Plugging in a value of 2, that is negative 6, so that holds. Okay, B, we have 1/2. This one's a little more complicated. Let me give it a little more space. Our first term is 1/2. Our second term is 1/2 plus 1/2 squared. We're adding 1/2 to that power next, and that is 3/4. Okay, and then the next term, if we do 1/2 plus 1/2, okay, we'll take that last term 3/4 plus 1/2 to cubed. That is going to be 7/8. If we add in, so 7/8 plus 1/2 to the 4th power, that is going to be 15 out of 16. Okay, so in general, it looks to be we have one less than our denominator. One less than our denominator. So our denominator is powers of 2, so that's 2 to the n minus 1 divided by 2 to the n. Written equivalently, that would be 1 minus 1 over 2 to the n. That is our explicit formula. Right, one more recursive. The first term is negative 4, and it appears to be adding 6 each time. So my sequence is negative 4, 2, 8, 14, etc. Alright, so an is negative 4 plus 6 times n minus 1, or 6n minus 10. Alright, next we have this idea of a limit of a sequence. Given a sequence an, if the terms an become arbitrarily close to a finite number L, as n becomes sufficiently large, we say that an is a convergent sequence, and L is the limit of that sequence. Whoops, that is meant to be that. Okay, so it's the limit of the sequence. In this case, we write the limit as n goes to infinity of an equals L, or simply an converges to L. If it does not converge, if it's not going in a direction, then it is a divergent sequence. Be familiar with those words there, convergent and divergent. All right, let's check out some examples here. All Alright, so here, these are graphed as the values of n are on the x-axis and the values of an, the sequence values, are on the y-axis. As n increases, it appears for A that it is divergent. It is just going off to infinity. It's not heading any particular place. Right, B looks like it's actually approaching 1. As n increases, it is getting closer and closer and closer to 1. It is sort of leveling off there. Right, C is totally divergent. It is going back and forth between -1 to 1, -1 to 1, -1 to 1. It's not actually going anywhere. And the D there, it's approaching 0. These values are going positive and negative, but they're bouncing back and forth and getting closer to 0. Those are some examples. Now, here's the formal definition of a convergent sequence. Okay, this should look very familiar. It should remind you of limits from Calculus 1, and that is the absolute value. So let's see, okay, let's start from the top. A sequence an converges to a real number L if for all epsilon greater than 0, there exists an integer n such that the absolute value of an minus L, previously that would have been f of x minus L, is less than epsilon if n is greater than capital N, greater than or equal to capital N. The number L is the limit, and we write the limit as n goes to infinity of an equals L, or an converges to L. In the case that this is convergent, okay, if this all holds, this is a convergent sequence. If it does not converge, then it's a divergent sequence, and we say the limit does not exist. So the idea is that after a certain point, capital N, the values of the sequence are as close as we want, that is, epsilon, to the value L. That's how you can interpret that. After a certain point, the values are as close as we want to this certain value that we're calling the limit. Alright, let's move on to the next thing. So now we already said that these are functions. Sequences are functions with a domain of the natural numbers. So that means that we can actually use some things from limits. Okay, the limit of a sequence defined by a function. If we can find a function that has the same values as our sequence, then we can just use our limit properties. So I'm going to, for each of these, consider whether it diverges or converges. And I'm going to redefine this. The limit as x goes to infinity of 5 minus 3 over x squared. If we had this function, then this second term will go to 0, and the limit is 5. Which means that an converges to 5. So I can take that function idea and then use something there and then backtrack to a limit. Okay, next, limit as x goes to infinity of 3x to the 4th minus 7x squared plus 5 over 6 minus 4x to the 4th. Okay, now we can use L'Hopital's rule actually because this is continuous and these are both going to infinity. One's going to negative, one's going to positive infinity. Or we can use an idea we've used from Calculus 1 that these terms are negligible. These terms don't change much. Oh, actually wrong one. These terms don't affect anything. All right. So in the long run, all that we really care about is 3x to the 4th over negative 4x to the 4th, which is negative 3/4. So an approaches negative 3/4 in this case. Part C. All right, the limit as x goes to infinity of 2 to the x over n squared. Okay, both of these are going to infinity, so we are going to have to apply L'Hopital's rule here. This is an indeterminate form. As x goes to infinity, that is going to be the natural log of 2 times 2 to the x over 2n. Still both going to infinity. I changed to x's in one and n's in the other. Okay, so let's fix that real quick. Now you can apply these properties with n's in there, okay, because they are a function defined in terms of n. Okay, now that does not help. So let's apply L'Hopital's rule again. X goes to infinity. This is the natural log of 4 times 2 to the x over 2, which then goes to infinity, which means we can write an diverges. It goes towards infinity, and the sequence is divergent, or just simply the sequence diverges. For part D, we notice that this is actually of the form 0 to the infinity. As the inside portion is going to 1, okay, we have to the infinity. So we are going to have to modify this just a little bit. Let's first take the natural log. So we're still taking the limit of 1 plus 4 over n to the n. By taking the natural log, because the natural log is continuous, we can interchange these. So this is the limit as n goes to infinity of the natural log of 1 plus 4 over n. And actually, let's go ahead and change these to x. That way we can apply some of our familiar tactics to it, which treat this as if it's a function without that restricted domain of the natural numbers. So 4x to the x, x is going to infinity, x goes to infinity, or x to the x. Now, a logarithmic property here will bring our x down. Now, what you're going to do is, this is still written in terms of infinity times 1, okay, or infinity times 0 because of the natural log there. So we are going to rewrite this. X goes to infinity. Okay, let's rewrite this as this quotient. Natural log of 1 plus 4 over x over 1 over x. Now we are in the form 0 over 0, an indeterminate form, so we can apply L'Hopital's rule. Take the derivative of the denominator and the numerator. Taking the derivative of the numerator, okay, is going to be negative 4 over x squared divided by 1 plus 4 over x, because that is the derivative of the logarithm, the natural logarithm. Alright, so once we put that there, we have a complex fraction, so divided by the derivative of 1 over x, which is negative 1 over x squared. Now rearranging that, this is the limit of 4 over 1 plus 4 over x. And the limit of that is 4. Now we can observe at this point that this says the natural log of our sequence is converging to 4. Again, the natural log is a continuous function, so we can actually go ahead and say that this means that an, the sequence itself, is converging to e to the 4. And that is it. Okay, so now this technique of using logarithmic properties to get something in the form of L'Hopital's rule is very handy, and it comes in useful lots of times. Alright, now let's move on to our next part. Letter E. Right, so the limit as x goes to infinity of 5x squared plus 1 over e to the x. Both are going to infinity, so we can apply L'Hopital's rule. Limit as x goes to infinity of 10x over e to the x. That does not help, so let's apply L'Hopital's rule again. It'll be 10 over e to the x, which that limit is 0. So an goes to 0. It converges to 0. Right, next, determine if each sequence diverges or converges. Well, because we have some continuous functions here, cosine is a continuous function, we can take the limit. If I take the limit, it goes to infinity, of cosine of 3 over n squared. applying my limit, this term goes to 0, which means this converges to cosine of 0 or 1. So an converges to 1. The square root function is also continuous. So we can take the limit of the square root of 2n plus 1 over 3n plus 5. This limit is going to 2/3. So the limit, or just an, converges to the square root of 2/3, which is the square root of 6 over 3 if you'd like it rationalized. So it converges to the square root of 6 over 3. Okay, determine if these converge or diverge. Okay, it's important to recall the squeeze theorem. We are going to be able to use that. So cosine is stuck between -1 and 1. -1 and 1. Cosine n over n squared. So that is between -1 over n squared and 1 over n squared. As both of these go to 0, this converges to 0 as well. Alright, the squeeze theorem is helpful when you have something that is alternating as well, because cosine goes from negative to positive, negative to positive. Well, this specific -1/2 to the n, that is bounded between 1 over 2 to the n, okay, and -1 over 2 to the n. In fact, it takes on those values in between. As both of these are going to 0, our sequence in the middle, an, converges to 0 as well. Okay, we have a new concept to add here, the idea of something being bounded. Oh, one more. Alright, so sine is bounded. In fact, I'm going to go ahead and write this as, that is 2 minus sine n over n. Okay, so sine n over n, that is bounded between -1 over n. So this is bounded between 2 minus 1 over n. Write that whole thing in there. 2 minus sine n over n, and 2 plus 1 over n. As both of these are going to 2, that means that our sequence an converged to 2. Okay, next we have the idea of bounded sequences. A sequence is bounded above if there's a number such that the sequence for every term is less than or equal to that number. Bounded below is the same idea. We have a number that's underneath every term. The sequence is greater than all of those, than that number for every term. Alright, a sequence is a bounded sequence if it's bounded above and below. Okay, if it's not bounded, we call it unbounded. Now this is a very important fact, this next thing. We have that a sequence, if it converges, then it is bounded. However, just because something is bounded does not mean that it converges. Okay, so you can consider something like that, the alternating sequence, what that's called. Bounces between -1 and 1. It's bounded, but it never converges. It's divergent. All right, next we have the idea of a monotone sequence. Something is increasing if each term, the next term, is always greater than the last term. It's decreasing if the next term is less than the current term. And then it's monotone if it's either one of those. If it's either increasing for all values past a certain point, or it's always decreasing. And here we have a theorem we are going to apply. If an is a bounded sequence, and there exists a positive integer n naught, such that an is monotone for all n greater than or equal to n naught, then the sequence converges. If it is bounded, and there's a point at which it's monotone, then it converges. So let's dive into one of these. Okay, now this comes in helpful with something like this. 4n over n factorial. Okay, so first, this term, this an, is greater than or equal to 0. It's always positive. There's no way you can get a negative number out of that. So it is bounded. It is bounded below. Okay, it's bounded below. And so now let's consider an plus 1. Factorials make this pretty nice. So 4 to the n plus 1 over n plus 1 factorial. Okay, now that is equal to 4 over n plus 1 times an. We have 4 to the n and n factorial. So that is what happens there. So the question is that decreasing? Is that smaller? And because this fact right here, because these are always positive, and this is going to 0, it is definitely decreasing. Okay, so it is monotone. Oh, we wouldn't leave that there. It is definitely monotonically decreasing. Okay, so because of that, we know that it does converge. There is a limit. All right, now what we are going to do next is a very common strategy. So the limit, as n goes to infinity, of an is going to be the same as the limit of an plus 1. Because in the long run, that's where they are both heading to the same place. So let's say that that limit is L. So applying that to this, what we have up here, we said L equals the limit of an plus 1. Well, an plus 1 is 4 over n plus 1 times an. Well, the limit of an is L. So this is going to 0, and this limit is 0. But first we had to use the monotone convergence theorem to tell us that it even converged. We have to know it converges first. Then we can apply some of these properties to it. All right, letter B, 12b. Okay, I have messed around with this sequence several times, okay, over the course of several days actually, and I've just sort of pondered it. And the first thing you need to do with these, since this one is recursive, is plug in some values and see what's going on with the sequence. Now, at a certain point, it appears that the sequence is greater than or equal to 1. At a certain point, it starts to appear that all of the terms are greater than 1. Okay, it took me a little bit to convince myself of that, okay, because, you know, it looks like it, but that's one thing. Having a suspicion is one thing. So, what I decided to do, and I'm going to walk you through what I decided, I think that it's greater than or equal to 1. So, I decided, you know what if it's less than 1? Is there a problem there? Okay, so I'm going to suppose that it's less than 1. Or I guess really that's an plus 1. An plus 1 is less than 1. Okay, so that's for some value of n. Now, I'm going to take that, replace that. That is an, let's see, so an plus 1 is an over 2 plus 1 over 2an. Multiplying through by 2an, I get an squared plus 1 is less than 2an, which means an squared minus 2an plus 1 is less than 0, which means an minus 1 squared is less than 0. Now, this means that I have something positive that is less than 0. That obviously does not work. So what that means, this is a contradiction. This means that an plus 1 is greater than or equal to 1. Or, yeah, I need to write that differently. An plus 1, that sequence, that term of the sequence, is always greater than or equal to 1. So let's use that fact. That means it's bounded. Bounded below by 1. That's important for our monotone convergence. Next we need to show that it is decreasing. So I'm going to go ahead and take this fact. So since it is greater than, okay, by the way, this is the same thing as an squared plus 1 over 2an. Okay, so if I take the fact that an squared is going to be greater than or equal to 1, then that means this is greater than or equal to 2an squared. Let me divide by 2an. That is the same sequence I have up there. So that is an over 2 plus 1 over 2an is greater than or equal to an. Or an plus 1 is greater than or equal to an. And that is going to be true for all values that I come up with. So this is decreasing. It is monotone. Good. So now I know that it has a limit. So now I'm going to apply that idea earlier. I'm going to take the limit of both sides, and this is going to, so I'm going to take the limit of each of these. Okay. All right. Now the limit for those two is actually going to be equal. Okay. That's the idea. Limit of an is going to be the same as the limit of an plus 1. So that gives me L over 2 plus 1 over 2L is equal to L. Yes, okay. So the limit of an is equal to the limit of an plus 1. N goes to infinity of an plus 1. Limit of an is an goes to infinity. Those two are going to be the same. So if I multiply through by 2L, I'm going to rearrange that. 2L squared, okay, and that is going to be equals L squared plus 1, which is only true if L equals plus or minus 1. Now, since our sequence is always greater than or equal to 1, that means that our limit is 1, and that is an converges to 1. All right, one more example in this section, and then that will be it. And it's recursive. All right, so I'm going to first sketch what this means. The first term is 1. The second term is the first term divided by 2, so 1/2. The next one is divide by 1/2, etc. Okay, so this is decreasing. It's multiplying by 1/2 each time. So an is equal to 1/2 to the n minus 1, which that's the same thing as 2 times 1/2 to the n. Okay, now that is always greater than or equal to 0, so it is bounded. Bounded below by 0. Now let's consider an plus 1. An plus 1 is equal to 1/2 to the n. Just by plugging n plus 1 in there, replacing n for n plus 1. Well, that is definitely less than or equal to an, because that's 2 times that sequence right there. Let me write that differently. That is less than or equal to 2 over 1/2 to the n, which is an. So it is definitely decreasing. It's monotonically decreasing. So that means we'll apply that same idea. It converges, so the limit of an plus 1 equals the limit, n goes to infinity of an. So that is going to be, the limit of that one is, well, they're both going to be L. Okay, so this is 2L equals L, which means L equals 0 and an converges to 0. Okay, that is the end of our work with sequences, but this is just the beginning. We are going to pick up with series in the next section, which is going to apply this, so we want to make sure we get these down good. That's it.